Hi everyone, welcome to week 9 of chemistry tutoring. Today we will be talking about equilibrium and mass action expressions. This will be from our chapter 13 in the OpenStax textbook. So let's get right on it. We will be working on question number 9. This is the one that you can hopefully see on your screen. And it reads, among the solubility rules previously discussed in the statement, all chlorides are soluble except for Hg2, Cl2, AgCl, PbCl2, and CuCl. Write the expression for the equilibrium constant for the reaction, represented by the equation, and it's that one right there, and as well as write the expression for the lead and the chlorine reaction. And it is asking us what the constant value will be, if it's going to be above 1, below 1, or equal to around 1. So let's first start by writing down the expression equation that we'll be using. And so to find the reaction quotient or the equilibrium constant, these two values will be the same at equilibrium. And so since we're at equilibrium and it is asking us to find the equilibrium constant, we can use the same equation for QC as for KC, because they will be both equal to the same expression. And that will look like this. So these are going to be the products, constants, divided by the reactants. And from this equation right here, what a generic expression will look like for a reaction will be something like this, Ma, so this M is just a coefficient of how many A molecules there will be, plus Nb goes to Xc plus Yd. And so like I was saying before, the m and the n and the x and the y are just coefficients. So when we are using this equation right here, these will be the exponents to the molarities of all of the reactants and product values. And so when you multiply it out, then you will get the constant for the equilibrium constant. So this reaction right here, the first one that we are working with, the AgCl goes to Ag and the Cl ion. We first need to write down what this equation will look like first, and then we can kind of predict whether or not the Kc value will be above or below or kind of equal to 1. So for the first one here, the Kc constant will be equal to the products, so that's the Ag, and then that will be multiplied to the power, or not multiplied, but that will be raised to the power of 1 because there are no coefficients, divided by nothing actually, because solids cannot be in the reaction quotient, they're not considered. And so because this reaction has more products to start with, you would think that it might create more products, but because this reaction, it starts with AgCl, and so this is a solid right here. And because it's on the left side of the equation here, it's not going to produce as many ions because it's starting with a solid. So whatever is going to be made, it'll be undissolved solids. And so there's going to be few products to be made. And so that's why the Kc value is going to be less than 1 here, because when there are fewer products made, the Kc value will be lower than 1. And so similarly, with the question B here, with Pb 2 plus, and then with 2Cl, goes to a solid PbCl2, it's starting with a lot of the ions, so it's going to be making a lot of the solids in return. So this reaction, just rewriting it, Kc will be equal to the products, but because the PbCl2 is a solid, we don't include that. So that'll be a 1 divided by the reactants. So that's the Pb2 plus. And then multiplied by the Cl raised to the power of 2. And that is raised to the power of 2 because there is a 2 coefficient on this chlorine ion right there. And so this is what the reaction quotient will look like, but in terms of what the Kc value will be, because there will be more solid to make from the reactants because it's starting with more ions, it'll produce a lot more of the products. And so because the products will be larger, then the Kc value will be more than 1 because of this factor. So unlike in problem A, you're starting with a solid, so you are going to be making less of the ions because of what you're starting with. And because in problem B you're starting with more ions, you're going to be able to make more solids. And so that is why these Kc values are the way they are. Okay, let's move on to the next problem. Let me know if you want to go over anything. So this is going to be on question 11. It says benzene is one of the compounds used as octane enhancers in unleaded gasoline. It is manufactured by the catalytic conversion of acetylene to benzene, and it has this reaction here. And it says what value of Kc would make this reaction most useful commercially. Kc of 0.01, Kc of 1, or Kc of 10. So let's think about this equation or this reaction first. So we have 3C2H2 goes to the gas. And because this is going to be on the product side and we're wanting to create more benzene, like I was saying before, when we have a higher Kc value, more products are going to be made. And since we want more of the products made commercially, we want to have a Kc value that is a lot higher. And because we are given the option of 0.01, 1, and 10, we would want to choose the Kc value of 10 because it would ramp production up. And so that's why the Kc value will be larger. So now let's move on to question 15. Question 15 says, write the mathematical expression for the reaction quotient Kc, or Qc, for each of the following reactions. So we are going to be working with 15A through E. So let's first refresh us on what the Kc equation looks like. So for A, let's work on that one first. So we have Kc, or Qc, and it'll be the products raised to their coefficient and then multiplied by each other, and then all divided by the reactants raised to whatever power they need to be for their coefficients. So specifically for A, because the products are going to be right here, that's going to be on the top part of the equation here. So we will have the CH3Cl, and that'll be that concentration, and then multiplied by the concentration of HCl. And because they only have coefficient numbers of 1, we will not be raising it to any other power other than 1, so we can just leave that alone. And so now let's move on to the reactants part. And remember always when you are writing down these problems that you're checking if any of the molecules or any of the atoms or anything like that are in their solid form, because solids are not included in the reaction quotient, only gases and liquids are. So the CH4 multiplied by the Cl2, and that'll be done with the product side. And so that is what the expression looks like. We aren't given any concentrations for any of these gases, so we don't need to solve anything because we're only setting it up for what the expression will look like. So now let's move on to B. This one is nitrogen gas and oxygen gas, making nitrogen monoxide. So let's start by starting with the QC. And the product side of this is going to be the NO gas. But since there's a 2 coefficient, we will raise this to the power of 2. So we are done with the products because only one thing is being made. And then the reactants portion, we have the N2 gas, and there's no coefficient, multiplied by the O2 gas. And there's no coefficient for that as well. So now let's move on to C. C, there's also only one thing in the product side, and so that's going to be the SO3. And because there is a 2 coefficient, we will be raising that to the power of 2, and then dividing by the reactants, and that's SO2 and O2. And because the SO2 has a 2 coefficient, we will be raising this to the power of 2 as well. So now let's move on to D. Okay, for this one, we have the barium, oxygen, and as well as sulfide. For the product side of this, because the BaO right here is solid, we will not be including that in the product side at all, or products or reactants. Since both of these are solids, we will not be including that. So what it'll look like is just simply the SO2, because that's on the product side, on the top. And there's no coefficient here. So that's simply what this QC value will look like. Now let's move on to E. And just as I was saying, how we don't include solids right there, because this product of the P4O10 is a solid, we will not be including that. So instead of having nothing up there, we will just put a 1 in replace of it. And for the reactants, we have the P4, and there is no coefficient, so no power raising here. But for the oxygen gas, there is a 5 coefficient, so we will raise that to the power of 5. And so that is that reaction quotient filled out. So now let's move on to the next problem. Okay, this one says the initial concentrations or pressures of reactants and products are given for each of the following systems. Calculate the reaction quotient and determine the direction in which each system will proceed to each equilibrium. So when we look at these problems, we should always be looking at the constant that they are giving us, because this is a QC value and this is a KP value, or this is KC and this is KP. And you will need to look at which one it gives you, because sometimes it'll give you the opposite and you need to convert to whatever you need to use. So let's just say, for example, they give you KC, but then they give you pressure values instead of concentration values. Then you will need to convert that before you can proceed with solving the problem. But for right now, looking over this, the KC value, it gives us concentrations, and the KP value, it gives us pressures. And that is what this constant needs to give in order to align with the units. So let's first work on 17A. And we are working with the KC, so we're working with concentration values. And so let's first write down the QC reaction, and then we can plug in the concentration values and then solve for it. So the QC will look like this. the products are on the top, so that we have N2, and then we have H2, and because there is a 3 coefficient, we will raise that to the power of 3, and then divided by the NH3 raised to the power of 2. And so it gives us the concentrations of each of these gases. So when we plug them in, it gives us for N2, it's going to be 0.2, and then times the concentration of 1 for H2 raised to the power of 3, and then divided by the NH3 molarity, which is 0.2 to the power of 2. And multiplying that out, we will get a value of, let's see here, let me make sure I wrote it down correctly. Right, the N2 value has a concentration of 1, not 0.2. There we go. Okay, so now when we multiply it all out, we will get a value of 1 divided by 0.04, and that will equal 25. And so that is the reaction quotient for this reaction, and it gives us the Kc value of 17. And because that is going to be less than the 25, it'll proceed reversely. So it'll go to the left. So reaction goes to the left because the Kc value is a lot lower than the reaction quotient. Okay, so now let's move on to B. And it'll have the same exact reaction here, so we can just copy down the same reaction quotient. It'll just have different values that it will give us. So same Kc or QC. And now we are solving with pressures. So instead of concentrations, we will be working with pressures here. So let's just edit that part of this. So the pressure of each of these. And we will still be raising it to the same power as we will with, finding out the coefficients and then matching that with the exponents. So just be aware of that. So when we're doing this, instead of concentrations, we are just using with pressures, so it's the same thing. So for the nitrogen gas, we have 2 atmospheres. And then for the hydrogen gas, we have 1 atmosphere raised to the power of 3. And the pressure of the NH3 is going to be 3 raised to the power of 2. And so solving that out, we will get a value of 0.22. And because the Kp value was 6.8, which means it's going to be less than the reaction quotient, it will proceed forward because it still can make more of the product. So that's why it proceeds forward instead of backwards. So now let's move on to 17C. So 17C has the reaction pointed out right here. And so now let's first write down the reaction quotient equation. So we have the products on top, SO2 raised to the power of 2 multiplied by O2, and there's no coefficient, so no exponent, and then divided by the reactants, so we have SO3 raised to the power of 2. And now let's plug in the Kc values, and we're working with concentrations and not pressures here. So for SO2, we have a molarity of 1 squared, and then for oxygen gas, we have 1 as well, divided by the concentration of SO3. And because in the problem it gives us the concentration of SO3 as 0, this is an undefined situation, and since it's undefined, it's going to actually go reverse. And the reason why this is the way it is, and it's going to be the concentration value, or the constant that it gives us is 2.230. is because when you have a value in the denominator that is proceedingly really, really, really small, if you divide something by a very, very small number, you're going to get a very large number. So it is undefined, and it technically is going towards infinity, and because it's so large, it's going to be a lot bigger than 0.230. And because it's going to be larger, it is going to react in the reverse direction of this reaction. So now let's move on to D, and it's the same exact reaction that we're working with. So the QC value will be of pressures instead of concentrations now, because it gives us the pressures of each of the gases. So we will have SO2 on the top, its pressure to the power of 2, and then O2 pressure divided by SO3 pressure. And I put a little subscript P to know that I'm talking about pressures, but you can write it in a different way that makes more sense to you as well. Because with concentrations, we always use these brackets. Brackets kind of separate it from the standard parentheses. So using parentheses, it does not signify any concentration, whereas the brackets do. But getting back to the problem here, let's plug in these pressures for all of these gases. So for SO2, we have a pressure of 1, and that is going to be squared. And then for O2, we also have 1 atmosphere. And then for SO3, we also have 1. So the problem here, or the answer is going to be 1. And because that is going to be less than the Kp value that it gave us in the problem, which is 16.5, it will act in the forward direction because it's a lot less than what the constant will be. So that is how we write down all of these equations and figure out which way the reactions will be proceeding in equilibrium. So now let's move on to the next problem. This problem is 19, and it says the following reaction has Kp equals 4.50 times 10 to the negative fifth at 720 Kelvin. So we have nitrogen gas added to hydrogen gas, and it makes NH3. If a reaction vessel is filled with each gas to the partial pressures listed, in which direction will it shift to each equilibrium? And so it gives us the pressures. And so it is going to be what we were doing in problem 17. So we first need to list out what the QC equation will look like, and then we can plug in the pressure values, and then we will compare that to the Kp value that it gives us. And if the Kp value is going to be below the QC value, it'll act in reverse, and vice versa, it'll act forward. So let's first start with finding out the equation. So the product will be on the top. So that's going to be the NH3, and that is going to be squared because of its coefficient, and then divided by the reactants. So we have N2 gas, and then multiply by the hydrogen gas, and that'll be raised to the third power because of its coefficient as well. And so after plugging in all of these pressures, we will find the QC value. And so let's do that right now. So we have 93 for NH3 squared, and then divided by N2, so that's 48, multiplied by H2, raised to the power of 3. And so on top it'll have 8,649 divided by 6749184. So that's going to be around 6 million. And so dividing those out, we will get a value of 0.00128. And that is a very, very small number, but the Kp value that it gave us is a lot smaller. And so this value will be larger than the Kp value of 4.5 times 10 to the negative 5. And so because it is a lot larger than the Kp value, that means it'll be acting in the reverse direction. So now let's move on to 25, and I'll leave that up there for a second if you're still looking at it. So 25 says convert the values of Kc to values of Kp, or the values of Kp to values of Kc. So we are working with 25a through c here. And so now let's write down the equation we need to convert these two values. So for the Kp, to convert it to Kc, it'll be equal to Kc multiplied by R times T to the power of the delta N. And so the N number here is going to be the difference in the product moles minus the reactant moles. The R is going to be the gas constant, and that's going to be equal to the 0.08206 that you've seen a lot, and then the T value is going to be the temperature in Kelvin. And then the Kc value is the constant for concentration, and then the Kp value is the K constant for pressure. So in the first problem here for 25a, we are working with a Kc value, and so now we will be converting to Kp. So for Kp, it'll equal Kc value, and it gave us in the problem as 0.5, multiplied by the gas constant, which is the 0.08206, and then multiplied by the temperature, which is going to be the 400 degrees Celsius that it gave us, but plus the 273.15, which will give us the correct temperature in Kelvin instead of Celsius. And then now we need to raise it to the power of delta N. And so delta N in this problem will be the product moles minus the reactant moles. And so in this specific reaction, for the products we have 2 of the NH3, so that is going to be the product moles subtracted by the reactant moles. And so for the reactant moles we have 1 N2, and then we have 3 H2. So we have a addition of 1 plus 3, and so that'll be 2 minus 4 for the difference. And then multiplying and raising everything to that power, we will get a value of 1.64 times 10 to the negative 4 as our Kp value. So now let's do the same for B. So now we will also be converting it to Kp as well. And so it gives us the Kc value of 50.2 multiplied by the gas constant, 0.08206, multiplied by the temperature, which is going to be the 448 plus 273.15 to convert it to Kelvin. And now we have to figure out the difference in moles. So for the product we have the 2 Hi. So we will have a 2 minus the addition of the reactants. And so we will have the 1 plus 1, because we have 1 H2 and we have 1 I2. So we have 1 plus 1. And if you wanted to kind of convert this strategically, the 2 minus the 2 here is going to give us a value of 0. And so all of this is going to be 1. And so it's 1 then multiplied by the 1. So our answer will be 50.2 because it's going to be raised to the power of 0. And so that's going to be the Kp value. Okay, now let's move on to C. And now we will be converting it to the Kc value. And so to get it to the Kc in the first place, we need to divide by, let's see here, we need to divide to isolate for this value here. So to get to that, we have, let's move this down first. So this is our standard formula, the Kp equals Kc RT raised to the power of n, but to get it to Kc, we will divide by both sides. And so divide that, and then it's Kp. Actually, if we divide this by that, then we can isolate Kc. So Kc, if we divide by RT, so we will get Kp divided by RT raised to the power of delta n. And so now that is going to be our equation that we will be working with to find Kc. And so now let's plug in all those values. So we will get a value of 4.08 times 10 to the negative 25, and then divided by 0.08206 for the constant, multiplied by the temperature, which is 25, plus the 273.15, all raised to the power of the difference in values of the moles. So now let's solve that. And so since we have a solid here, we will not be including that. So same with here, these two are both solids, and the only thing that we can count again is going to be the gases and liquids. And because the gas is on the product side, it is going to be 10, and then minus nothing because everything else is in its solid form. So that will be raised to the power of 10. And so now I'm going to solve that out just to make sure we get the right answer here. So it's 25 plus 273.15 multiplied by 0.08206 raised to the power of 10, and then the 4.08 times 10 to the power of negative 25 divided by that number, we will get a value of 5.30 or 5.31 times 10 to the negative 39. And so that is going to be our answer for C. So now let's move on to the next problem. And we are working with 52 here. And it says, what is the value of the equilibrium constant at 500 degrees Celsius for the formation of NH3 according to the following equation? So we're working with nitrogen gas and as well as hydrogen gas, making NH3. And it says an equilibrium mixture of NH3, H2, and N2 at 500 degrees Celsius was found to contain 1.35 molarity of the hydrogen gas, 1.15 molarity of the nitrogen gas, and 4.12 times 10 to the negative 1 molarity of the NH3 gas. So let's first write down the equation that will find the equilibrium constant, which is the Kc. And because it is going to be at equilibrium, it says an equilibrium mixture, the Qc equals the Kc. And so that's the same equation then to solve for them. And so just as we did before, the products go on the top. So we have the NH3 molarity raised to the power of 2 because it has a coefficient of 2 divided by the reactants. So that's going to be the N2 multiplied by the H2 raised to the power of 3. And so now let's plug in all of our molarities. And for NH3, it says we have the NH3, we have the 4.12 times 10 to the negative 1. And so that's raised to the power of 2 divided by the N2 molarity multiplied by the H2, which is the 1.35, and that's going to be cubed. And so multiplying all of that out, we will get a value of 0.035 0.59992227. And so to round it off to 3 significant figures, we will get a value of 6.00 times 10 to the negative 2. You could keep it in standard form or scientific form, either or, but that is the value of the Kc, of the equilibrium constant. And sometimes, just to note, it will give us the temperature value, but we may not need to use it because we don't need to convert it to Kp to Kc. Just as we were doing here, we needed the temperature to convert these two constant values, but because we didn't need to end up using it, don't let it get in your head like, oh, they gave this piece of information to me, I have to use it. Sometimes that's not the case. Sometimes they give you more than enough of information and you have to figure out what you need to use in the first place. Okay, now let's move on to 54. So 54 says a 0.72 mole sample of PCl5 is put into a 1 liter vessel and heated. At equilibrium, the vessel contains 0.40 mole of PCl3 and 0.4 mole of Cl2. Calculate the value of the equilibrium constant for the decomposition of PCl5 to PCl3 and Cl2 at this temperature. So for this problem, we first need to write down this reaction because we need to figure out if we need to find any coefficients, because that will change our equation, because we might need to put an exponent on a certain value that we're trying to find. So for PCl5, we started with this. So that is going to be on the left side of the equation. And it's going to PCl3 and PCl, or just Cl2. And so let's see if it's balanced. We have 1p over here, we have 1p over here, and for Cl we have 5. And for on the right side we have 3 and then the 2, so we have 5 Cl as well. So this is all balanced. So that's good to know. Now we have the reaction. Now let's solve for the Kc. And so the products go on the top. So we have the PCl3, and we're working with molarities here, times Cl2 molarity divided by the PCl5 molarity. And so now we can plug all of our molarity values in here. So the PCl3, it says we had 0.4 moles, and then for the Cl2 we have the 0.4 as well. But for PCl5, it's actually not just straight up the 0.72, because we started with 0.4 moles of the other in the other things in the vessel. So we actually have to subtract that because we don't have that completely. And so now we can solve that out, and that will give us a value of 0.5 for the Kc value. And so I'm going to double check to see if that's the right answer, because it's always good to double check. Yep, it gives us 0.5. Okay, let's move on to 60. So 60 says, complete the following partial ice tables. So we are given this one for A, and so it's important to note what they have already written here. So we will find out why that's important in problem B here, but because they put it plus 1x, that means they haven't changed any of the coefficients here, because there's only 1 mole of the O2, so we will need to only add plus x, so only 1, because there's only 1 mole of the O2. And because the ratios are all kept here, we can leave it alone. And so because we're gaining O2, we also gain plus 2x for the SO2, because there's 2 moles of it. So we gain 2 moles of it each time, because if we're proceeding to the right, we're going to gain products. So we're gaining the products of the O2 and the SO2, and so the coefficients change to how many moles we are given of the specific molecules. And so for the reactant side, the 2SO3, there's two of it, but the reactants are changing. So we're losing the reactants to, not losing it, but the reactants are changing into the products. So the reactants will lose its shape or lose what it was before. So it's going to be a minus 2x because of that fact. And so now let's move on to B. And the reason why it's important to notice any kind of like ratios that are going on here, because for this one, it says plus X, but for 3 molecules of the O2. So this must have been divided by 3. You can keep, so just as long as you keep all of your additions, all of your changes the same, that is okay. But if you change one of them, like if you divide it by 2, you have to divide by all of your changes by 2. And because the 3 right here was divided by 3, we have to divide everything else by 3. So for the 4NH3, it will also be added because the way this is going, this says this like, this way and this way arrow sign, reactants and products can, it can switch places where it'll go to the left or to the right on the reaction. And because the reactants are gaining, the reaction is actually proceeding to the left, not to the right. And so because the reactants are gaining in this situation, we will also add, but because there's 4 of the NH3, we will add a 4, but we need to divide it by 3 because this x right here is secretly 3 over 3x. And because that's what's going on, we have to divide everything by 3. And so now let's move on to the product side. And so we will lose minus 2, but because there is a 3 ratio happening here, so we will need to divide it by 3 by x, or multiply by x too. And then for the water gas here, we will subtract, because it's going to be moving towards the reactant side of this problem, 6 divided by 3. And so that will just be 2. So 6 divided by 3 is 2. So that is how you have to deal with figuring out if anything is being divided by a certain factor. So you have to keep it the same all across the side, because like I was saying, everything was divided by 3 for the coefficients. Okay, and so that is the last problem of the day today. Let me know if you have any questions. As always, this will be posted to the PSU Learning Center's YouTube channel, and you can make comments there as well. Feel free to let me know if you want the textbook as well. I can always link that down on the YouTube or here as well. I'll stick around for a couple minutes. But if there isn't anything else, I will see you all next week for, I think, the last week of chemistry tutoring for 222. Thank you so much.